Chapter 12, Matrices. We're finally on to the last section, 12.4, Matrix Methods for Square Systems. By the end of these 3 videos, we're going to know how to solve a system a different way than using the RREF of the augmented matrix. But first we have to learn about what? I'm Jim and I'm Joe. Jimbo and Jobo. And today we're here to learn about what? I don't know. Well, you guys are blocking it. Oh, sorry. Square matrices. Yay. Alright, so let's talk about square matrices. First of all, what is a square matrix? Well, it's probably something you could figure out on your own. It's a matrix that's square, so that means the number of rows has to equal the number of columns. So it is an n by n matrix. There's a special matrix called the identity matrix, which has to be a square matrix. So it's n by n, and it has the special property that it is all zeros. All the entries are zeros, except it has a diagonal of ones, and the diagonal of ones goes from left to right. So for example, if we have a 3 by 3 identity matrix, what would that look like? It would be 3 by 3, and it would be all zeros except this diagonal row would be 1. So it would be 1, 0, 0, 0, 1, 0, 0, 0, 1. And why do we care about an identity matrix? Well, you know, when we're talking about multiplying 2 matrices, what's cool about an identity matrix is if you take any matrix that's square and multiply it by the identity matrix, you get the original matrix. And you could test that out if you wanted to. I'm not going to do it here in the notes, but you could take a 2 by 2 or 3 by 3 and multiply it by its 2 by 2 or 3 by 3 or whatever, n by n identity matrix, and you'll get the matrix, the original matrix back. So that's going to be important. You know, whenever we define multiplication, it's important that we have an identity that brings us back to the original matrix, original thing. All right, we're going to use square matrices to represent square systems. And a square system is just a system of equations in which the number of variables equals the number of equations. And that's most of our systems of equations. Most of our systems of equations are square systems. So for example, we have in a system like this, x minus y plus z equals 0, 2x plus y minus 3z equals 7, and 3x minus 2y equals negative 4. Now, if we represented this, and this is a square system by the definition, the number of variables we have is 3 variables, x, y, and z, and we have 3 equations. So this is a square system. But if you think about the augmented matrix for this square system, it would be a 3 by 4 matrix because we would have the coefficients, and then the constants would be their own column. So you would have 3 rows but 4 columns. That's not a square matrix. But what is a square matrix is the coefficient matrix. So a matrix of just the coefficients, which would look like 1, negative 1, 1, 2, 1, negative 3, 3, negative 2, and what goes in here? Well, it should be the coefficient of z, and there's no z here, so it should be 0. I concur. You guys are right, it's a 0. So we do get a square matrix there for the coefficient matrix. And then what we'd really do is put the constants in their own 3 by 1 matrix, but we'll talk about that in the next video. Now what we're going to want to do to help solve this system is to find the inverse of this coefficient matrix. And some square matrices have inverses. Not all of them do. So how can you check which ones have inverses? So what you do is you look at the determinant and if the determinant is not equal to 0, then it has an inverse. Now, how do we find the determinant? Well, first of all, you can only find the determinant of square matrices. So if you have, let's say, a 2 by 2 matrix like this, or that's A, then the determinant of A would be A times D minus B times C. That should kind of remind you of the dot product, if you remember from vectors. And vectors and matrices are related because a lot of times we'll use matrices to represent vectors, but that's not really important to remember at this time. Also, probably if we do anything bigger than a 2 by 2 matrix, then it's really hard to figure out the determinant. It's kind of complicated. So we're just going to use the calculator. What? The calculator? Yeah, this guy is going to show us how to use the calculator to find the determinant of anything bigger. So 2 by 2 you could do it by hand, it's pretty easy. But anything bigger than a 2 by 2, like a 3 by 3, you're going to want to use the calculator. So let's get the calculator here. Alright, remember first, do the matrix menu. Alright, so first we're going to enter our matrix into the matrix. So turn on your calculator, clear anything out. And we're going to go to second matrix, edit, second matrix, edit, and matrix A is going to be 3 by 3. And it looks like I've already inputted this one correctly. So we have 1, negative 1, 1, 2, 1, negative 3, 3, negative 2, 0. All right, first thing I want to do is now find the determinant of this. So go back to the home screen, and now we're going to do second matrix math, and the very first choice is DET, which is short for determinant. All right, so we're going to choose that. Determinant of matrix A, and then hit enter, and we get a negative 4. And what we want to make sure is that is not equal to 0 before we try to find the inverse. Now, once we've determined that it has an inverse, this one has a determinant of negative 4, which is not 0, so it has an inverse. So all that we are going to do is do names, matrix names, get our matrix, and then use the negative 1 here. X the negative 1. So the inverse of matrix A is notated as A to the negative 1. And again, that's not an exponent. It's a lot like the function notation where this negative 1 isn't an exponent, it's indicating inverse. So this means the inverse of matrix A. And why do we care about that? Well, if we do matrix multiplication of an inverse times itself, what do we think we'll get? All right, well, let's find out. First of all, let's see what this inverse matrix looks like. And there it is. And a lot of times this is going to be in decimals. And what you might want to do is see it as fractions if you care. If you want to see it as fractions, just do what you just did. Oopsie. So matrix A inverse, and then send it to fraction form. And how you do that is just hit the normal math menu here. And the very first thing is send to as fractions. So choose that. So I'll do the inverse of A as fractions. And here's the same matrix as that one, just in fractions instead of decimals. All right, so there's our inverse. But the question was, remember, what happens if I do a matrix inverse times the matrix? And I will get, look at that, the identity matrix. So if I do an inverse times a matrix of itself, I get the identity matrix. All right, we're all done. Let's clean up out of here.